I'm here today to talk to you about maybe ways that robots could help us live happier, healthier, and more productive lives. It's actually only been 1 year, so it's in part, yeah. It's in part like what analyses I've run and what additional results or studies I have since last time I came and talked to you. So some of it may look familiar. I'll use some of my past work as grounding, but I'm also hoping to share especially some of the newer projects that are starting up in my lab and ways that I'm taking these old project directions and turning them into something that I'm pursuing here at Oregon State. So just to remind you, I think almost all of you have seen this slide, but of my general background, a while ago I was studying at the University of Cincinnati, both mechanical engineering and Spanish, which I used more than one would realize. After that, I studied at the University of Pennsylvania, pursuing a master's in robotics and PhD in mechanical engineering and applied mechanics. There, I was also lucky to be part of an IGERT site program at Penn that was focused on complex scene perception, so I got to learn a lot about experimental psychology as well, which, as many of you who are focused on human-robot interaction will know, it's very useful, good to know how to design studies in that space, among other things. After that, I was a postdoc at the University of Southern California, and throughout all of these things, I also have this strong identity as a performing artist, so performing music and comedy and other types, even playing in pit orchestras of theater productions. It's all very important to me as well, and you'll sort of see this throughout the various work that I'll share. You'll hopefully see ways where performing art ability or entertaining ability in the systems that I'm deploying can help them to succeed and help them to compel people. So just to ground this research in some background areas that are more central to what I'm doing, one area that feeds strongly into my work is haptics. So this is a field looking at the human sense of touch. In particular, in my work, I often think about how humans perceive touch and how we can flip this and help robots to perceive things in an intelligent and touch-capable way. Entertaining interactions also come into play in this work, thinking about how, as we interact with systems, robotic systems in the everyday world, they can actually be compelling and not annoying or frustrating to use. I've seen studies and I've experienced studies failing because systems are frustrating or unclear to use. So this is an important thing to consider as well. And I also think about socially assistive robotics. So this is ways that the unique abilities of robots can help to motivate people to do things like exercise more, or learn, or make healthy decisions, maybe things that we know we should be doing anyway. For certain populations, these things can be especially hard. So how can we use robots to help address that problem? And I've touched on work all across this space, so I'll quickly animate some past work that I've done in case one of these areas is especially interesting, but I don't come back to it later in the talk. So I've thought about things like how robots can use haptic adjectives, how a robot might be able to touch an object and then label it as squishy or compressible or hard or slippery. That's some fairly vintage work that was published at ICRA a long time ago. I've also thought about intuitive haptic teleoperation. This is interesting and has ties to all kinds of different work. We might want to teleoperate or remotely control robots in various environments. So here we added different haptic feedback to a teleoperation controller and actually had pretty good luck letting someone from across the hall teleoperate the arm of a PR2 robot. So some interesting work there. I'll talk more about infant motor practice, which is one of these pieces of work that falls more purely in the socially assistive sphere. I've also thought about things like distance learning via telepresence. So this I presented a while ago at Human-Robot Interaction, and I have some other work coming out about that soon. We were thinking about how you might be able to use a telepresence robot to help students who need to miss extended amounts of school to stay connected to the classroom, both in an educational but also in a social sense. In entertaining interactions, for a while I've been thinking about this and even worked with Heather to put on a Kai workshop a couple years ago. That was an interesting way to engage with the community as well. between socially assistiveness and entertainment, I did one study on mischievous robots. So this was kind of a fun deluge into a sub-area involving both of these fields, where we could look at whether robots that can be mischievous might be more compelling to people or seem more intelligent or agentic. The proceedings of that conference still haven't been published, but I think they will soon. It's one of those ISRR papers that trails quite a bit. I've also looked at human-robot clapping games, so ways we might be able to combine playful entertainment and haptics, how we can equip a robot to play in those games, and the effects of different leadership assignment strategies in these types of activities. And human-robot exercise, which I'll come back to later, that sort of encompasses all three of these areas. We have human-robot social touch. There's a socially assistive application where keeping people active is a challenging thing, something a lot of people know they should be doing anyway. And entertainment too, so as we're designing these games, they should actually be fun and interesting to play. So a lot to think about. I can't possibly do justice to all of that work throughout this talk, so I'll pick certain sub-areas, but you'll see in this presentation that my central goal is kind of to create better everyday robots with social and physical abilities that do help them, hopefully, to help us live healthier, more productive, and happier lives. So we'll sort of return to this theme at the end and see how I've done so far and maybe where I'll be going in the future. We can use this to sort of ground the structure of this work as well. But one idea that sort of connects this idea of using robots to help us live happier, healthier, and more productive lives to the present state of robots. We're already seeing images, especially in cinema and even in plays, of robots interacting with people in social ways that also involve some sort of physical interaction component. So I think it's safe to say that as robots appear in more everyday human-populated spaces, people will expect them to be able to do this sort of thing, sort of arm wrestle or do a fist bump or use other types of playful social touch. So it's important that likewise robots are actually able to do these things. And many themes from my work feed back into this. This task is not without its challenges though. In human social physical interaction, we see challenges like a mismatch of models. Here they don't know whether they're going in for a high five or a fist bump. So some interesting perception problems here. Maybe the failure to perceive that your teammates don't want to high five you, you're too good at football, no one cares anymore. There might be safety or privacy considerations as well. So if we're building a high-fiving robot like in this Microsoft SkyDrive commercial, this is an actual commercial that aired, so a vision of perhaps how a high-fiving or socially, physically capable robot might become unsafe to its environment, to nearby people. So as we're trying to equip these personal robots in everyday spaces with better skills, we run into a lot of challenges, not just in understanding how we can apply these systems, but also in being capable in more traditional areas of robotics as well. So it's an interesting mix of the two, and I'll do my best to weave a story of what I've been doing so far, how different themes from robotics tie in, and how different results that I've found along the way might inform us as to the title of my talk, whether robots can help us live happier, healthier, and more productive lives. And we'll kind of use this Venn diagram and sub-areas of it as an outline for the talk. So I'll cover 4 main areas of research in the presentation today. The first is trying to understand social touch. So based on those sort of video examples and future-looking applications of social touch between people and robots, how can we start to break down that type of interaction and understand how aspects of the control and planning underlying these robotic systems might help them succeed or affect how they're perceived by people? I'll return then to that human-robot exercise idea. So this is one research area right in the center that combines all 3 of these general research areas. We'll see what happens there and how effective we can be in human-robot exercise. I'll then talk a bit about infant motor practice, so a way we might be able to use a small humanoid robot or other types of robots to help infants practice healthy behaviors. For infants especially, it's important to have all kinds of social and physical and cognitive exercise to promote normal development, so that's an interesting area to delve into as well. And I'll talk a bit about robots in art. So again, this is an area that I think can feed back into all of these other types of research to help robots be more interesting and compelling and pleasant to interact with. So we'll see what we can learn there. But to start out, we'll dive into this first topic of understanding social touch. For most of you, I think this topic in particular will look familiar, but here a general idea is that those underlying control and planning strategies for a robot that's capable of social touch are important. They can have implications on the perceived personality of the robotic system and perhaps influence whether people will want to continue interacting with the system, among other things. So we see in some past work, in handshake work, for example, we've seen cases where the facial expression, different physical properties and planning properties of the handshake can influence the perceived emotional state of the robot. Even in handovers, we see this. So if a robot's passing an object to a person, the robot releases the object sooner than expected, it might seem to be careless. If the robot holds tightly onto the object past when the person expects, it might seem possessive. So there are sort of affective or personality implications of these planning and control strategies for robots. We also know that people are just really good at a very wide variety of these types of social touch interactions. So barely without thinking at all, people can produce interactions like this. I don't know if I could do all of these, but maybe some of them. Still pretty impressive. But even if you think about high-fiving your friend, you're pretty good at that, although there's a lot of underlying challenge in perception and timing involved there. So the central research question here is whether we can start to understand control and planning strategies for robots to begin to endow them with this type of skill, as we think this type of interaction might be expected or might emerge in various everyday environments. So again, this might look familiar, but to start to investigate this research, we programmed a Baxter research robot to be able to do this type of interaction. It's kind of a safe, repeated hand clapping motion. Baxter in particular, I think, is a good choice for this type of research, although the company has since gone under. It has both physical safety constraints, so the series elastic actuators making up the robot are particularly safe to interact with, even at 4 a.m. debugging code on the robot. It also has some software safety features where if it feels an impact of sufficient force, it stops moving, for example. So kind of an interesting design. I learned yesterday that a company has purchased the rights to Baxter and Sawyer, so perhaps not the end of the road for this robot. It's called CoThink Robotics. Classy. So the motion that Baxter's producing here is actually human-inspired. In work previous to this step, we had put accelerometers and position trackers on people, had them do this type of interaction, so we had a reasonable underlying model for how Baxter might do this. We also built a custom end effector, so something reasonable and safe to interact with at the end of the robot's arm. We developed a control strategy to help Baxter move fairly quickly. If you've seen industrial robots move, you might be thinking, this is pretty fast for an industrial robot. I'll bring up that control equation later to emphasize what's going on there, but that took a bit of time to figure out as well. In addition to contact detection strategies, so we were able to use some ideas from past haptics research to figure out how we might identify the timing of the hand contact. In this case, actually using the wrist accelerometer of the robot was sufficient for that. We could take the root sum of squares from that and do thresholding, but in other cases it may not be that simple. You can learn more about this if it's interesting too. So in the end, we had this human-robot hand clapping interaction that was safe, and we could start to manipulate aspects of it to begin to investigate that question that I presented earlier, how control and planning during this interaction with the robot might influence human perception of the robotic system, especially in the affective realm. So the three things we manipulated in this case were the facial expression of the robot. In some conditions of this study that we ran using this interaction, the robot would maintain this sort of neutral, mildly positive face the whole time. In other conditions, the robot would change to this more responsive face, sort of acknowledging that it felt hand contact, then returning to the neutral face about 0.1 seconds later. So kind of a sign of haptic intelligence there. Another thing we manipulated was the physical reactivity of the robot. So this is more on the planning side. Can we sense hand contact and then actively plan a retreat trajectory after that? In the top plot here, you see the physically unreactive case, where the joint angle that's being plotted is the wrist 1 joint of the robot, sort of here on my arm. You see X's when we sense hand contact, and you can also see that we adapt our strategy, whether we try to maintain the same trajectory regardless of sensed hand contact, as shown in the top, or actively plan a retreat trajectory, as shown in the bottom. The series elastic actuators also lead to interesting artifacts in that plot. And stiffness-wise, this is another thing we manipulated more on the control side. So I asked Kevin questions about this last week. I'm also using this PD controller with feed-forward torque and gravity compensation. But in this case, as we're trying to alter the stiffness effectively of the robot, we can change the proportional gain to a few different levels for that active wrist 1 joint to result in a different sort of perceived stiffness. Sure.
So, the question, so the desired trajectory, was that programmed by you or was that inferred?
So that was programmed by me, but based on the human motion model. We saw that the motion of people was generally fairly sinusoidal, and we also saw that the amplitude of their hand motion increased at lower frequencies of clapping. Yes, so these are the things we manipulated. Over this overall design space, we got sort of a 2x2x2 set of conditions, so 8 different types of interactions you could experience with the robot. Again, this is what the interaction in each trial of this study looked like. And after each interaction of this type, we asked people to rate 4 things about the robot: the perceived pleasantness, energeticness, dominance, and safety. So this is sort of based on psychology theory, a 3-axis space that's often used to represent affect. We were also curious about safety just because at all times we wanted to know how people felt as they were interacting with the robot and if any type of interaction felt particularly unsafe. We asked some free response questions as well, which I won't dive into too much in this talk, but there is some more detail about our results in this fairly new journal article, among other places. And one key insight that we got here after running different statistical analyses was that the facial reactivity was one aspect of the robot that we could manipulate to increase robot pleasantness and energeticness. A facially reactive robot seemed significantly more pleasant and energetic based on some ANOVA tests that we ran on this data from the study. We also saw that arm stiffness could influence independent parts of the perceived affect. So a higher arm stiffness actually affected perceived robot safety and dominance. This result was a bit counterintuitive. A higher stiffness actually made the robot seem less dominant and more safe, which was sort of the opposite of what we thought going in. It's possible that this relationship isn't completely linear. It might be that there's a sweet spot for stiffness of the robot arm, but in this case, exploring just 2 different stiffness levels, we did see the lower stiffness seemed more unsafe and less dominant, which was interesting. As I start my lab here and begin to spin up some research projects based on social touch, I'm taking a bit of a step back. So in the 5 or 6 years since I started this work, there have been a lot of other interesting pieces of research presented. So things like that work that Guy Hoffman mentioned a few weeks ago, the tactile skin display with spikes and goosebumps, things like HuggyBot, these 2 especially are fairly recent. There's some human-robot handshake work. I'd say overall that's the most common type of human-robot social touch research. And things like the haptic creature, which has also existed for a while, but I think at UBC they've been doing some subsequent work on that system. So I think there's a fair amount out there, and it's a good time to take a step back and sort of do a survey of what's out there as we find future research direction possibilities in the social touch space. So I'm working with Brian Zhang right now to do a survey of social touch. I think it'll be an interesting contribution to define what the future application areas are. By the way, Haptic Creature is much bigger than you expect. If you're a Star Trek fan and have recently watched The Trouble with Tribbles, that's about the right scale of size of the Haptic Creature, and it does look kind of like a Tribble. So as I get started here, I'm working on this survey, and I think that'll be an interesting, informative step to figure out what the next big thing in social touch will be and design research appropriately for maximum contributions to the field. At the same time, we're carrying on some of the other types of work that combine different parts of those overall areas that I mentioned. So I'll next talk a little bit about human-robot exercise and what I've done in this space so far, and other ways we're thinking about adult health with the help of robotic systems at present. So in this space, there are some challenges emerging. We see in the literature that older adults are among the most sedentary of populations. This can happen for a variety of reasons, but it's a challenge that is perhaps first worth addressing. If we're able to keep older adults active, we can see gains not just in the physical realm, but also in the cognitive. But there is a challenge here in limited resources. So there isn't necessarily the amount of physical therapy resources needed to keep these older adults active or to give them personal training as they try to stay active. So an interesting question that emerges here is whether robots might be able to help with this. So can we use social touch or intelligent robotic systems to motivate older adults to do light exercise, which might lead to different types of gains for their ongoing health? So here we worked with a physical therapist, an occupational therapist, a rehabilitation robotics researcher, and a game designer to try to design interactions that were sort of akin to things in the state of the art of physical therapy and also appropriate and reasonable for older adults to carry out. We designed 8 different exercise games, and we shared these games at first through a few different forums, some late-breaking reports and demonstrations to the community. We were also interested to show the games to the community and see what people thought and whether we could learn more about the state of the art of human-robot exercise by sharing with other robotics researchers. So trying to work with specialists in the field from the very start of this research. And through interactions with those experts, we designed 8 different games. So you won't be able to see them too well here, but they're the Mimic, Stretch game. I'll show you some videos of some of them later. The Teach game, the Agility game, the Strength game, the Hand Clap game, Roboga, and Flamenco. So 8 different games. You can maybe get a rough idea of what they entail, either by their names or by the frames shown here. Some of them involved human-robot touch, and some of them didn't. Later on, we thought it might be good to have a bit of a variety so we could do some hypothesis testing on the effects of social touch. But for now, we actually aim to do more of an exploratory study. So we've designed these games with specialists in areas like physical and occupational therapy. We designed them along a few different intended criteria. So we wanted to vary things like how engaging the game was, how cognitively challenging, because for an older adult, with Alzheimer's, for example, it might be important to encourage more cognitive practice. They might be physically healthy already. Physical challenge as well. You might have the opposite, where someone's cognitively very well, but needs to be encouraged on the physical side. And cooperativeness. So different game premises, I think, can be more or less motivational to people with different types of personalities. So trying to explore this space and design games with different combinations of these aspects. And using these games, we did an initial exploratory study, bringing people in, getting them to play the games, getting their feedback on the games, gathering different types of data. So overall, we brought in 20 younger adults, 19 older adults, and we had all of them play all of these exercise games. Again, with kind of an exploratory focus, but a few things we were especially curious to know. One was what the unique advantages might be of each of these games. We also wanted to know how the older adults in particular would experience the games. So in the end, we were designing the games with them in mind, so perhaps differences between the younger and older adult experience could indicate whether we designed them appropriately or who the target audience for the games might actually be. So we also measured a lot of things to help us evaluate the games in these ways. Actually, just a ton of things. So different types of clinical assessments, surveys, sensor recordings from the robot, and video recordings. And we could extract different types of insights from these various data. They helped us run a set of various types of analyses. So here's some videos of the games themselves. Audio might help. I don't know if it's working. You can see from the video, though, that this is more of a Simon type of game. So the human is teaching the robot a pattern of clapping motions. So after collecting all those types of data and doing different types of quantitative and qualitative analyses, we found from this game that people sometimes needed a few tries to understand how to play the game. It was a little more cognitively challenging in that way. It was clearly understood to be competitive, which was our intention though, and it also led to the most reports of self-efficacy, either through comments from users or from free response feedback from users on the surveys that we administered. So perhaps a challenging game, but something that could lead to more feelings of fulfillment, which can be important as people try to age with dignity. This is another of the games, the agility game. Here, a user is trying to make sort of rapid contact with the end effectors of the robot, and the premise is sort of trying to wake Baxter up. And this game was really interesting. Actually, it made people work a lot harder than we expected. They hit the robot harder and more frequently than needed for the game logic. It also led to sort of the most happy reactions, the most dialogue with Baxter, and people started to compare Baxter to their family and loved ones in this game. So kind of interesting effects of a game that actually in premise is pretty simple. Just to go through a few more games, I'll just show you the results from 4 of these, but if you're interested, I'm happy to tell you about more of them. This was one of the non-contact games, the Roboga or Robot Yoga game. So in this game, the robot struck a sequence of held poses, and the user would match those poses and hold them for about 5 seconds. This game was pretty close to our design expectations. So those different axes that I mentioned previously of physical and cognitive challenge, cooperativeness, and engagement. The game was pretty simple to grasp, but it also was effective in encouraging exercise in participants, especially in terms of muscle burn. A lot of participants mentioned sensations of exercise. So kind of simple but effective in certain applications that might be best. And then this was the flamenco game, where you can't hear the flamenco music, but Baxter's dancing along to, what is it, Malagueña? And doing a series of dance poses, teaching the person, and then the person reciprocates those sequences of poses. This one was also pretty well understood by us. Users rated it on different scales, close to our design expectations. And it also led to some playful interaction and banter with Baxter. Some people did self-reflection of their ability to dance, but they also sort of chided or bantered with Baxter as well. So different types of interesting social interactions. Some games were less social, but better for encouraging exercise. So depending on what we're trying to do with a patient, maybe important insights to consider in selecting games from a superset of possible physical therapy routines. Another thing of interest was that difference over age that I mentioned. Again, we were designing these games for older adults, although in the example videos, I show a younger adult interacting with Baxter. That's partly since it's being recorded, but I do have videos of the older adults interacting if you're curious about that as well. So one thing we weren't sure of was whether older adults would even interact with the robot in this way. In the study we found all of the participants in this exploratory study were willing to play all the games with Baxter. So this is kind of a useful insight. Yeah.
How did you recruit them? Did you just maybe, by the very recruiting process, end up with older adults who would be interested in it?
It could be. There's always a risk in studies where you're recruiting participants that people who enroll are more interested in the area. We did find in this population, though, that at least I think over half of the older adults were non-technical in a question that we asked them in the demographic survey. And they also had little or no experience with robots. So although they may have selected to enroll in the study because they were interested, they also maybe didn't know what they were getting themselves into and didn't have that much experience with robots. So at least a semi-promising result. It could be interesting, perhaps in more up-to-date steps to work with an assisted living facility, put something like this in a common space, and then see when people are in more of a natural environment, whether they would interact with the robot. That's something I'm thinking about for the future. We also saw some differences across the two age groups, looking specifically at that. So we saw higher ratings from the older adults in all of these areas. Some of them are to be expected. Some of them just confirm that these exercise games are probably more appropriate for older adults than young, healthy adults. So things like higher exercise level, pain or muscle burn level, energy and engagement level, those probably mean these games are more appropriate for older adults. We also saw older adults exploring more space in the Teach game. I didn't show you a video of this one, but it involves sort of music composition where the arms of the Baxter robot are an input device. So you can explore different arc lengths to try to find different musical notes in the workspace of the robot. And they also rated themselves as performing worse, which also means they had more room for improvement and perhaps the games are more challenging. That's good if we want to be able to promote self-efficacy through this type of activity in the future. You can read more about these some other places too. But overall, I think an insight here is that older adults are indeed a better target audience for this type of game, and they're experiencing more levels of exercise and muscle burn pain, which in the end sort of helps to show the promise of this type of interaction. Although there's more to go, doing some of those follow-on studies in a more naturalistic environment could be really interesting and are part of the next envisioned work that I might do with that type of interaction in particular. As I don't have a Baxter robot yet, though, we're still thinking about adult health in different ways. So right now, one thing that Brian Zhang has also been considering is ways that a Cosmo robot could be used as a workplace coach to encourage healthy behaviors at work. I don't want to tell you too much for reasons I'll mention in a moment, but if you haven't seen the Cosmo robot before, you can see it moving in the center left of the screen here. So it's a pretty expressive little robot that's marketed as a toy, but also has a nice API and can be connected to different sensor systems in everyday environments like Brian's desk and workspace. So we're looking at ways this robot might encourage healthier workplace behaviors. We're planning to run a study on this soon, so I won't tell you too much about our hypotheses, but you should look out for a call for participation in this research. And if this is the kind of thing you might be interested in and you work in Graph Hall, you might be eligible. So that's all I'll say about that for now. I want to shift gears to another health-related area, but this one's looking at much younger participants and falls more into the purely socially assistive robotics space. So here we're thinking about infant motor practice. And again, there's some underlying health-related motivation here, where at least in the United States, almost 10% of infants are born at risk of some developmental delay later on, and early interventions in various spaces can influence a large part of overall infant development. Despite this need, though, the standard of care is often to wait until a later age to supply any intervention. So interventions for very young infants, that's a space where we might be able to make a big difference with robotics. We also see infant tendencies. In infant developmental psychology, we know that contingent reward learning is something that can be used to encourage infants to move in various ways. We also know that infants tend to imitate, although the definition of imitation and results of these studies are sometimes contested. But we want to use these two behavioral phenomena to try to design a robotic system that can encourage infant motion. So here the research question is whether we can do that using what we know about challenges in infant development, but also emergent behaviors in infant development. Can we use a small robotic system to encourage infants to move in a particular way? And this could be good since motion intervention can have implications on the cognitive and social development of infants as well. So here's sort of the interaction scenario that we were envisioning, perhaps a Now robot sitting facing an infant who's wearing different types of sensor systems. We did a study involving a setup like this, bringing in 12 infants from the greater Los Angeles area, supplying 3 different reward types from the robot. So in the contingent reward literature, often providing some interesting type of reward when an infant does something can make them do that more. We were leveraging this idea here. Many of you know, if you've ever interacted with infants, that they also have a fairly short attention span. So 3 different rewards. I'll tell you more about how they were ordered and how long each one went on. But changing that up a bit was actually important to keeping infants engaged, even in a fairly brief study. And we were trying to teach, in particular in this case, a knee extension kick. So this is something that the age range of infants we were looking at, 6 to 8 month olds, might be starting to do, but it's not as common as sort of a downward kicking motion that infants of that age would do more frequently. So trying to encourage them to actually do this, that's an interesting thing we can study as they do that more. It's a bit outside the realm of what the infants of this age range would most typically do. So in this study, we brought in those 12 infants. In each of the sessions, there were different phases of the study. The first of these was a baseline phase. So during this period, the robot sat motionless, and we wanted to get a feel for how much the infant would move and how they would move without any rewards or incentive from the robot. So that's helpful for defining sort of the usual state of behavior of the infant, at least in a way. We had a demonstration by the robot. So like I mentioned, we wanted to leverage both imitation and reward learning in this interaction with the robot. So one thing we're doing with the robot that makes it a convenient choice that we selected the Now is the ability to model behavior. The robot's about the same size and has about the same motion capabilities as an infant. So the robot can model this kicking behavior at the start of the study. Then we started with different reward phases. These overall went on for 8 minutes. Again, very difficult to run studies with infants. And each reward ran for 2 minutes and 40 seconds. So here, whenever the infant's moving with sufficient leg acceleration, the robot provides a reward, which in this case is a kicking motion. In other phases, we had a kicking motion with lights, or a kicking motion with laughing sounds or sound from the robot. So looking at different types of rewards, and we also gathered different types of data. These leg warmers on the arms and legs of the infant housed inertial measurement units that could help us collect acceleration and gyroscope information. We gave the parents surveys to find out how they thought the infant was behaving, which reward they thought was the infant's favorite, and whether the infant was moving more or in different ways than they usually did at home. And we took video recordings so that we could later annotate those as well, noting which types of kicks the infant was performing. Since from the IMUs we could figure out whether leg motion of sufficient acceleration was happening, but we didn't necessarily know what type of kick was happening. And skeleton tracking for infants is still a challenging and not quite solved research area, as many of my colleagues would tell you. Key findings here, we noted a few interesting things relevant to that question I introduced at the beginning. Can we encourage motion using a small humanoid robot? From some previous work, we found that infants look at the robot when it's moving. This makes sense also if you've interacted with infants, but it is important too, since if the infant weren't paying attention to the robot, we might not be able to encourage behavior change using rewards. Looking at the different phases of the study, we did see a significant increase in motion between the baseline phase of the study and any of the 3 reward phases. So the 3 reward phases weren't significantly different from each other in this space, but we did see significantly more motion overall. So this is looking at all of the infant motion together. A little more detail about this plot. Looking at each infant's behavior individually, so like I mentioned, we took that baseline information of how an infant might more typically be behaving and moving when a robot wasn't present, or at least when the robot is stationary and not supplying rewards. So in this case, we can look at the amount of motion in the baseline period. The standard in the contingent reward learning literature is to multiply that by 1.5, and if infants move more than 1.5 times the baseline reading in each of the subsequent phases, then they per se have learned the contingency. So in this case, 9 of the 12 infants learned the contingency, and they responded to the contingent reward with more motion, almost always in all 3 reward phases. Only 2 infants responded to the contingent rewards in only 2 phases, and in those cases they responded less to the motion and lights for one reason or another. We also saw that 9 of the 12 infants imitated the robot. This was leveraging a similar definition of imitation, so looking at the amount of ball kicks in the baseline phase, multiplying that by 1.5, and looking at the ball kick motions in the subsequent phases. This, our collaborators in physical therapy are a bit more skeptical of. I think, as I mentioned in the imitation literature, there's not a satisfying definition of imitation. So if you're interested in imitation, I think we need help as a community to define that in a more strong way. But at least in this case, we're following roughly the state of the art and the recommendations of our collaborators in kinesiology and physical therapy. And we see roughly that infants were imitating the robot more, again in 75% of cases, although there may be some room for improvement in how we're defining that. If you're interested in this, it'll be the cover article in an upcoming issue of Robotics and Automation magazine, so we're pretty excited about that. And one overall insight we can draw from this is that it does seem for certain that a small humanoid robot can encourage motion from infants. It remains to be seen exactly how a robot of this type can encourage imitation, although in this case, using our definition of imitation, we did see imitation in 75% of cases. It can be hard to be objective in that realm as well. That's one reason for doing video coding and for defining a pretty detailed code book of what we're annotating for in the video. And yeah, it takes a lot of time, but it can be interesting. So some next steps in encouraging motion here at Oregon State with the collaboration of Sam Logan, we're thinking about another type of young child mobility. In his research, he thinks a lot about encouraging mobility and providing new motion capabilities for young infants around the same age of the infants I was working with at USC. In this case, he's looking at infants who don't have access to commercial wheelchairs. So he's been building these really cool ride-on-car systems that essentially are equipping infants of that age range with the ability to have a motorized wheelchair type tool that they can use to get around. One thing that they've seen in deployments of these systems, though, is that over a 90-day deployment, the family and the infants in question might use the system for about 7 days over that entire time span. So that challenge might arise for several reasons. In the first phases of this research, Sam has been asking questions of these families to try to learn more about why this might be happening. But overall, we think this might be an area where the introduction of robotics could be useful. A few of the reasons for this lack of use might be the lack of peer interaction. So the child has mobility for the first time. They don't always know what to do with it. In fact, in some existing studies of power wheelchair users, when 4-year-olds are getting power wheelchairs for the first time, they behave in a less social way if they haven't been social in the past. So having some sort of peer interaction could be useful. Sam's also seen that parents don't always know how to play with their children in these types of systems. They have some recommendations like setting up a mock car wash, having the child go through, but having other ways to play with the child, perhaps with the help of a small mobile robot, could be interesting. So the beginnings of this work in his lab has involved attaching kind of an interesting reward, may seem similar and resemblant of that past work I mentioned, onto these ride-on cars. So in this case, there are proximity sensors around the car. If a peer or anything else comes close to the car, the reward goes off. There's an interesting sound and lights and bubble blowing. So this is a way we could maybe structure interactions between young infants and robots in a way that could encourage the infants to use the systems to move in different ways. This could be useful for a variety of reasons. Here's just a video of the system working too, where we can see the system itself does seem very interesting to participants in this playgroup. For now, they're most interested in the bubbles and lights and sounds, it seems, but if we can get young children near each other, they might end up socially interacting as well, so that's something we could investigate more rigorously later. But it seems there is interest and promise in providing these types of rewards, perhaps on a mobile robot, to children who are using these power wheelchairs for the first time. So we might envision a system kind of like this. In fact, I'm probably starting to work with a master's student very soon to develop a system like this, something like a TurtleBot with some intelligent navigation capabilities with an interesting reward on top. Using the same types of infant behavior phenomena that I mentioned in the past research, we might be able to encourage infants to move in certain ways with this type of reward. We know from this power wheelchair past work that there's a set of tasks that infants have to sign off on or master before they use these power wheelchairs more freely. So perhaps a robot could help a child to train in these areas or to accomplish these training tasks. This might lighten the load from caretakers and other intervention specialists who would usually be introducing the child to these systems. It also provides another type of advantage. So with the introduction of a robotic peer who's helping the child learn these things, we might be able to reduce sort of helicopter parenting and very hands-on interaction from the parents as children are starting to use these ride-on car systems, and that can be important for prolonged use and more independent use as well. So a few different ways we envision this work kind of going, but it'll be interesting to see where that goes, and I'm excited to start working with Sam on that project. So yeah, we're almost out of time, but I'll briefly talk a bit about robots and art as well. So like I mentioned at the beginning of the talk, we have these different focuses for projects in haptics and social haptics and socially assistive robotics, but designing compelling and capable systems in all these domains is important since we want people to continue using them. We want them to use these systems often for extended durations, and the systems have to be easy and intuitive and not frustrating for this to work out. So it's worth considering in that space then how we can make robots more pleasant and interesting and fun to interact with. As you might know, Oregon State is now the world leader in robot comedy, where Heather has blazed the trail for a long, long time. And at the end of living in Los Angeles, I was curious to dig into this space a little bit as well. So there are several reasons you might want to try to do this type of work. One that's particularly notable for me as a human stand-up comedian is that the forum of stand-up comedy is kind of a convenient space where we can do experiments almost by accident. Human stand-up comics tell jokes. They tell jokes in acutely different ways. They'll change just one word. They'll take recordings of themselves. They'll try to analyze in various types of ways whether the changes in the joke succeeded. So I think this is a convenient space for running sort of happenstance open world studies with robots. So that led me to want to ask this, at least briefly, as I was playing with robot stand-up comedy while still living in Los Angeles. I wanted to know if we could develop a robotic stand-up act and evaluate the impact of different humor strategies, particularly timing and adaptivity. So especially in Los Angeles and here at the Majestic Theater, they were also interested in this type of thing. It's pretty easy to find a lot of comedy events going on. Almost without trying, you might accidentally run a user study even. Just a lot of open mics and comedy shows going on all the time. And in designing a robotic stand-up comedian, in this case I was trying to design it sort of using the same sensing modalities and techniques that I, as a human stand-up comedian, would use. In particular, in lots of types of comedy clubs, the lighting is so bright that you can't actually see the audience. So one thing I didn't actually use was any sort of facial expression recognition, knowing that in all kinds of the top tier comedy rooms, you can't actually see the audience's faces. But I did consider things like timing. So as a human comic, I am not able to talk over laughter of the audience. As you've probably noticed, and perhaps people in the corners are suffering from, my voice is not very loud. So in this case, I often think, am I audible? Will I be audible if I continue telling my routine at this moment? If yes, I can continue. If no, I wait maybe up to 5 seconds. Perhaps greater than that would be awkward. Adaptivity is another thing that I note. So if a joke succeeds, you might do a tag or sort of an add-on joke that acknowledges the success of the joke or that tells another joke in that style. If the joke fails, there might be a chance for redemption, so changing the audience's opinion by making a joke about how they didn't respond or why they might not have responded. So again, we can sort of use this logic to create an underlying state machine for a comedy robot, just like past works in this space have. So did the audience laugh? If so, positive tag. If not, maybe a negative tag. If you're in the middle, you don't have to do a tag. As a human, this is a sort of logic I use as well. So again, it's pretty easy to do a lot of shows in Los Angeles. I took John the Robot to 23 shows. We did performances across a 2x2 space made by crossing those different possible combinations. So do we have that adaptive timing on or off? Do we have that adaptivity or tag selection on or off? You never know how many shows you'll get either though, so it's not a perfectly balanced set of performances in each of these condition combinations, but a pretty good number where we could maybe start to learn things about the effects of robot comedy on the audience insofar as these different timing and adaptation strategies. So from raw audience laughter, we see a few things. We saw that a robot with good timing was actually significantly funnier to the audience. We didn't see this with adaptivity. That could be for a few different reasons. It could be ingrained in the writing. Maybe the writing of the tags wasn't as good as the writing of the jokes. Maybe the robot is funny no matter what if it's performing capably, especially with good timing. We did see that robot adaptability, or these tags, could change an audience negative or lukewarm reaction to a positive one though. So looking at cases where audiences responded in a meh or a negative fashion, we saw that we're able to flip the audience response in almost 50% of cases, where they either laugh or respond in a meh way to the tag. So that's kind of fun. I think from this we can learn that a robot with good timing is funnier, at least in this application of stand-up comedy performance. And adaptability can also save different robot jokes. And again, this can feed back into the idea of robots in everyday spaces, where maybe we want our exercise robot to be able to make jokes. Maybe our workplace assistant robot should have a sense of humor. So I think that's important to consider. In the realm of robot art, we're also thinking about a few things here at Oregon State. You may have seen this robot around, but we're looking at robots in visual art as well. Here, my student who's working on this is really interested in generative art, so he's drawing inspiration from different generative artists and also contemporary abstractionists. He knows much more about this than me. But overall, our goal here was to make a minimalist robot that could generate art and that could also collaborate with people. So again, if we're able to put a robot in an everyday human-populated spaces, if we're able to put a robot there in a place that's almost expected, we see all kinds of kinetic art and other types of lobby art already in our everyday life. So can we put a robot there that's kind of minimalist, that won't change the scenery too much, but that'll change it just a little bit and allow us to manipulate things and overall learn about people's expectations of these everyday robots. So that's what we're interested in here. If you look at the robot drawing or the robot system at large, we call it the large-scale generative mark maker, and it's pretty minimalist, as I had mentioned. I'll zoom into a couple key components of the system. So here we have, for example, eye hooks in the extreme corners of the system. Some pieces of fishing line are threaded around these. At the base, we see 2 stepper motors and a microcontroller, so we can use that logic there and the motors themselves to lengthen or extend the fishing line, moving this pen-holding gondola around the canvas. So a few things going on there. We can watch it draw and be very impressed too. So this is the robot down in the wood shop in Fairbanks Hall, drawing one of its pieces of art. We're interested in a few things here. In this case, we were trying to use a pretty massive canvas, so up to 6 feet by 26 feet. So just the scale of the piece of art is pretty impressive and maybe different from things you see outside of a gallery space. Another thing here is the process of being able to watch the robot create the art. So this is another thing you might not usually get in a gallery. You can come visit the gallery at one point, see the drawing half done, come back later and see it look very different or have developed a significant amount. So those are kind of interesting things about these pieces, even before introducing human interaction. But as I mentioned, in this space, I'm most interested in how findings from these interactions between people and robot art can feed back into other areas of my work. So we wanted to introduce some interactive elements. I again won't tell you too much about this one, but you can see that the overall physical system is about the same, but now we have a podium with perhaps different input devices. And people can interact with the robotic art. I won't tell you too much about why this is, but this is sort of one of the rings that was being drawn on the canvas there with different types of artifacts from human interaction. We're going to put this piece up in the hallway on the 3rd floor of Graph soon so that all of you can interact with it. So I won't prime you too much to think about it in one way or the other, but you can know we have a large-scale generative mark maker. We have some interactive elements in this newer version of the robot, and you should go check it out if you're interested. So overall, at the beginning of the talk, I posed the question of whether robots can help us lead happier, healthier, and more productive lives. Just from the results of this work I've presented, I think we've seen some evidence that robots can help us lead happier lives, whether through the pure stand-up comedy or the ability to manipulate robot interactions to make them seem more pleasant. We've also seen some health evidence. Being able to encourage motion from infants is one way that we can overall improve the health of large groups of people. Through older adult exercise, perhaps as well we could, although it will be interesting to see in a more natural environment how people might interact with that type of robot system. And productive, I think this might be more of a second order effect. So as we apply some of these technologies or look at, for example, the workplace robot, can we see if there's a change in productivity in those computer users or programmers? I think this is more yet to be seen, but closely tied to the vision of some of these pieces of research. So that's all I wanted to present. This work wouldn't have been possible without the help and input of a lot of different people, including the current students I've been working with here at Oregon State, in places like the Wood Shop and the Majestic Theater, where we put that second installation of the drawing robot. And yeah, that's all. Thanks for your attention.